Greetings of the day, everyone. We are pleased to present our topic AQI prediction using geospatial object detection. Myself, Asma Sheikh, and with me are Tahir Afsar and Krish Thakkar. This project was guided by Dr. Kriti Srivastav. We are from Department of Computer Science Engineering, specialization in data science. The agenda of the topics are next. The motivation behind this project stems from the limitations of existing AQI systems. Many areas lack real time monitoring due to sparse sensors, and most models don't account for dynamic pollution sources like traffic. Our project tackles this by estimating emissions based on vehicle detection from satellite imagery, combining with the ground sensors. A scalable, more accurate AQI prediction contribution system for smarter urban planning. The literature survey. For the literature survey, we have studied almost 14 papers together and came up with the idea that the whole literature survey was divided into two major parts, the object detection and the AQI prediction. For the object detection part, the retina net and SSD and satellite imagery showing promising results. For example, in 2020 paper, using retina net achieved MAP of 0.72 and F1 score of 0.94. However, this model struggles in crowded urban settings and dataset limitations restrict broader scalability. For the AQI prediction, several machine learning models were explored. For the paper 2024, study combined gray wolf optimizations with decision trees, achieving up to 97% accuracy in Indian cities. The another approach used the AQNet model, fusing satellite imagery, NO2 data, and demographics. While these are accurate, most model fails to include real-time traffic emissions, a gap we aim to fill. Next, the gaps in the existing world work will be explained by Tahir.
So, moreover speaking, we have multiple gaps in our existing work. Firstly, there is no actual system which combines the AQI prediction and object detection and accumulates it at one place. So our so the so what our system does is that it gives you the contribution of vehicles to the AQI of that particular area. And apart from these gaps, the other gaps are that spatial resolution issues. In our scenario, uh, getting a geospatial images of a particular area is very difficult because the current sources which we are currently relying on are of different resolutions, and these resolutions uh, are not suitable for the detection of vehicles. Similarly, we have cope up with multiple gaps which have been discussed in this table. Yes. So basically, our problem definition is that current AQI systems depend upon the ground-based sensors, and we can't get an actual value where we can tell that how much is the contribution of vehicles to the AQI of that area. So our approach, which accumulates both of this in at one place, is we get the geospatial images of that particular area, calculate the vehicle prediction, and on based of that, we understand the AQI. We compare the AQI of vehicles and the ground-based sensors, and then we come to a conclusion of the actual contribution of vehicles to the AQI of that area. This is the proposed design. This will be explained by Christopher.
So this is a fundamental architecture of our system. Starting with the phase 1, we gather the data from the SkyFi API and the ground-based sensors, and this data are passed to the data pre-processing phase. In the data pre-processing phase, we are using normalization technique to encounter the error, and for the image, we are using a pixel-based normalization technique, and for the ground-based sensors, we are using a column-wise view to reduce the errors. This data are further passed to the two modules. First is the vehicle detection emission, and other is the data integration layer. The sensors data are passed to the data integration layer, and the images data are passed to the our YOLO model. In our YOLO model, it basically detects the vehicles and classifies the vehicles, whether it is a car, truck, or a motor vehicle. And each vehicle classified is mapped to a particular emission value. For example, a truck has a higher emission value compared to the car, and this emission value is calculated using the EV formula, which is mentioned in this slide. This data are further passed to the LSTM model and conv-LSTL model. By gathering this data, we are calculating the AQI for that particular region by using this AQI formula. Further on, this AQI gathered is uh, passed to our model, and from that we are predicting how much of that particular vehicle is contributing to the AQI of that specific region. This slide explains the same architecture. These are the gaps in the existing architecture, and we have overcome these gaps. This will be explained by Tahir.
So, moreover speaking, these are the gaps. Firstly, limited spatial coverage. In ground-based sensor, the radius is very limited of that sensors, and we can't get the actual accurate AQI of that area out of these radius. So, this is being overcome and achieved by us with the help of geospatial images. Further talking about, we have built this new approach, which is the integration of geospatial images and the ground-based sensors to get a proper and much better accurate value of the contribution of vehicles. This is our result analysis. So our product is in such a way that from our mobile app, a user can select any location, maybe his current location or any location on the map. Based on this location, our model will detect the AQI contribution of that area and then display it back to his main screen with number of vehicles, uh, which can be differentiated into buses, cars, or trucks or motorcycles. This is our training and validation loss of our model's accuracy, our YOLO model's accuracy. These are the test cases. In the test cases, I'll just explain one of the test case. The first one, which is the Austin, USA test case. Therein, the location that we have selected is a remote place where there is an industry. So in this scenario, the AQI is obviously high of that area based on the factors of the industry, but vehicles are less contributing factor to this AQI. So you can see over here that vehicle contribution is very less, which is 15%, because the AQI contributing factor over there was the industries. Uh, yes, we have also written a research paper and put it for publication. The application is still under processing. Hope that it gets selected.
So the novelty of this R architecture is that basically F is basically the activation function. D is the ground data fusion. H is a hybrid model, and M temporal is our LSTM model, and M spatial is our YOLO model, and F is basically a software activation function. So these are the references we have used for this project. Thank you.